You're looking for an assignment or an announcement titled Science2H task for U4L15. The do now, I want you guys to use that projectile FET one more time. I know you're probably getting sick of this, but you'll use this to answer a few questions on a Google form. So the link to the FET is right there. And then the next link, U4L15 do now, is just a Google form. There are just 4 questions to answer. And the instructions of what to do specifically with the simulation are in there. I'll give us about 9 minutes to work on that and keep an eye on the responses as they come in. I'm listening, so let me know if you have any questions or anything, but otherwise just take the next 9 minutes to work on the do now, and then we'll come together to review. Go for it. So I was looking through the responses, and most of you seem to be feeling pretty good about content from the previous part of chapter 5. So first of all, in the very first setup, did the projectiles that you fired at 60 and 30 land in the same place?
No.
They didn't, which is weird because this is exactly what we learned about this in the previous lesson. 60 and 30 add up to 90. We actually tried firing the cannon with those 2 angles in our previous lesson. So what is different here? Why aren't they landing in the same place? Most of you got this.
The altitude.
Yeah.
Yeah, the cannon is not horizontal to the ground where the projectiles are landing, right? So that's one of the requirements for that rule to actually work, is that the projectiles are landing horizontal to where they were fired from. And this question came up because I made this mistake after reading the chapter. I was like, oh, that's really cool. I pulled up the simulator and I started firing projectiles from different angles, but they weren't landing in the same place. And it literally took me a few minutes to be like, why isn't this working? And I was like, oh, I'm so dumb. The cannon is not level with the ground. So that's one of the requirements. The other one is that there's no drag, which is the next question. However, just kind of some silly ones in between. If you're able to hit the little David statue below the cannon, what angle do you need to fire at?
75.
Good. 75 works. What else works?
Like it was negative 45 or something like that.
Yeah, negative 40, right? So as usual, there's always 2 angles that you can get at, right? Now, 75, negative 40 are not going to add up to 90 in any way. But again, that's because our cannon is not firing at a target that is level with it, right? And so I was looking through your answers and got some entertaining answers for the third bonus question about why are they using a statue of David. Measure how high something is. Chose him because he looks dope. He does look pretty dope. It's fun to hit things. You got some violent people here, I guess. So doesn't look like anyone is getting at it though. My other classes, usually at least one person kind of got it.
I don't know. I haven't submitted it yet because I wasn't finished. But I thought that wasn't he a painter? And I don't know. Maybe it has to.
Michelangelo, who carved the David, was very famous painter and statue. But so getting at the size thing, has anyone been to Florence? Has anyone seen the David? Is it to scale? Is it life-sized? It's actually enormous. It's probably about 17 meters tall, which is one thing why it's so amazing, because he carved a pretty proportionate human. Like the hands and feet aren't quite to proportion, but it's very, very big. So that's not exactly why it's there. So you kind of have to know your Bible for this one. Does anyone know what David is famous for in the Bible? What did he do?
Oh, he fought Goliath.
Yes, and does anyone know what he fought Goliath with?
Like stones?
Yep, little sling. So in other words, he was throwing projectiles at him, right? You guys get it? Projectile motion. So I don't know for sure why the David's there, but that was the one thing when I looked at it, I was like, all right, that's probably one reason why they use that. The programmers are probably being nerdy. So anyway, okay. And so for the last question, when we bring drag into account, do the projectiles land in the same place when they're fired at 30 and 60? Which again is weird though, because you would think, is drag acting on both projectiles? I mean, it's not like it wasn't acting when you fired on the 30 and on 60, right? Drag was always in place. So you would think that drag, they'd still land in the same place. It would just be shorter than where it would originally be. But apparently for some reason, the way drag affects altitude and range, it actually alters the path. And so I don't know if maybe in the simulator there'd be slightly different angles that we could still get them to land in the same place consistently, but I just thought it was kind of interesting. So that 90-degree rule only works from horizontal position of fire and landing, and if there's no drag taken into account. All right. Before we move on to new content, I did want to give you a chance to review some of the homework questions. So hopefully you submitted your assignment. If you have not done so, please do so as soon as you can. But any questions or anything you left blank or were confused by from questions 21, 23, 24, and 25 at the end of chapter 5?
I wasn't sure about 25.
25, the very last question. So 25 depends on 24. So let's look at that really quickly. 24 is why will a projectile that moves horizontally at 8 kilometers per second follow a curve that matches the curvature of the Earth? To answer that question, remind me, every 1 second, how far is the projectile going to fall downwards? Anyone remember?
5 meters.
5 meters. And does anyone know how far down the Earth curves for every 8 kilometers?
5 meters.
5 meters, right? So it's going to match the curvature of the Earth is the key thing. So that's what that's getting at. So 25 says, then why is it important that the projectile in the preceding question be above Earth's atmosphere? If you were to fire a projectile inside Earth's atmosphere and you wanted to get it into orbit, it's not going to work. Why? What is the projectile immediately going to encounter if it was fired in the atmosphere?
Air resistance.
Yeah, so there's
Friction
drag.
wave.
Yeah, there's drag, there's air. It's going to start going through the air, and that's going to generate friction, and that's going to slow it down. So it's never going to be able to orbit consistently if it's inside the atmosphere. You can also think about there's mountains, there's trees, there's buildings, right? The atmosphere is full of stuff that it could impact. So this is why satellites, space shuttles, all that stuff, we get them at least 150 kilometers up where there's no more gases. There's very few other things that it could run into. So that's what 25 is getting at, is to avoid air resistance, avoid friction due to moving through gases. Angela, does that help? I think it was Angela asked that question, right? Yep, cool. Good question. Any others? Okay. I just want to go through a short slideshow summarizing key takeaways from the last section of chapter 5.12 on elliptical orbits. Feel free to take some notes on your digital notebook or on paper if you want. I have posted a video of myself going through these same slides, but I want to make this a little more interactive. I'm going to try using some poll everywhere questions. You might have used this in other classes, but it's kind of a quick response app. You can use your phone, or you can use the computer that you're on. You just need to open a new tab on a Internet Navigator. But again, we will chat more about that when we get to it, which will be very soon. So it's over here. Okay. So the last part of chapter 5 is all about elliptical orbit, which you can see a picture of right here. This is what most satellites are actually orbiting in. Yeah, Earth and the Moon also follow elliptical orbits. I'll talk about geosynchronous orbit and what they call escape speed, but I prefer to call it escape velocity. And that's getting at the idea, you've all heard that term before, of what goes up must come down. Well, if you achieve escape velocity, that will not be true. And so this is kind of a silly picture, but if you were to actually throw a baby up in the air at escape velocity, that baby would just continue on into space. So hopefully not something anyone does soon. First question that I'd like you to try answering with poll everywhere is, what are satellites? And you've got 4 options here. So if you haven't used poll everywhere before, there's 2 ways to answer it. You can either just pull up a new URL on your whatever your internet browser is. So if you're using Chrome or whatever, just make a new tab. The address is at the very top. You can see respond@pollev.com/hatesci2. So if you go to that address, it should literally pull up this question and you can select your answer. Or if you just want to use your cell phone, there's text instructions right below that as well. So you could do either one. So again, the question is, what are satellites? Option A, communication machines launched into space by humans to operate our cell phones and TVs. Option B, moon and only moons are around certain planets like the Earth. C, any projectile moving fast enough to fall continuously around Earth. Or D, man-made machines that take pictures from the surface of the Earth from high above. So I'll wait until we get at least 4 total responses, or 10 total responses. There's about 13 of us here in the class. Let me know if you have trouble getting it to work or can't figure out what to do. I'd like to try to get to at least 10 responses. Is anyone having trouble getting this to work like that? Is the URL not working or not sure what to do?
Yeah, mine's just taking a bit of a while to load.
Okay. Yeah. All right. Okay, well, let's look this up, see how we're feeling. There we go. All right. Yes, most of you looks like you're feeling good about it is indeed C. Any projectile moving fast enough to fall continuously around Earth. That is the definition that your textbook gives it as well. But I put in A, and a lot of my other classes, quite a few students chose A because that, I think, when you hear the word satellite, that's the image that often comes to mind is those kind of weird metallic looking solar panel covered machines that we tend to fire into space to, use for telecommunication and TV signals and things like that. But in reality, you can describe the moon as a satellite. Earth is a satellite that is moving around the sun. So it's sort of a catch-all phrase that describes all of those different, any celestial body that is orbiting something could be referred to as a satellite. All right. Okay, so the next few things I want to talk about, again, I want to just remind you that we're always assuming that what we're talking about, if it's Earth, that the satellite is orbiting at least 150 kilometers, if not more, above Earth. And again, why is that? What are we trying to stay outside of?
Air resistance.
Yes, right. Stay outside the atmosphere, so there's no, no gases that are slowing down our projectile. Okay, so in order to become a satellite, something that is continuously falling around the planet, the minimum speed required is 8 kilometers per second with no drag acting on it. And that's going to generate what's called a circular orbit. But in reality, most things in orbit aren't perfectly circular. They're actually traveling a little bit faster than 8 kilometers per second, and that forms what's called an elliptical orbit, where the satellite basically overshoots the mark. It falls away from the planet or whatever it's circling, but then it eventually comes back. And so rather than getting a perfect circle, you get this sort of wider circle. That's what we call an ellipse. Mathematically speaking, an ellipse has two foci or two focus points. Now, in terms of what we're going to talk about with gravity, there's really only one focus point that's exerting all the gravity on this single satellite rotating around. But you can draw an ellipse if you've got some string and paper and tacks or something. If you put one tack down and another tack down close by, attach them with string or floss, and then make it taut using a pencil, and then just draw in a circular motion. That will give you a nice even ellipse. And so what gets interesting is what happens to the speed of satellites when they're moving in an elliptical form. And so I want you to kind of take your best guess on this. This is the next poll everywhere question. I'm only going to give you 3 of these. But just take a guess at this one. Question is, how does elliptical orbit affect the speed that a satellite as it travels? So option A is there's no effect. Speed of the satellite is consistent, does not change throughout the elliptical orbit. Option B, it goes faster as it approaches and passes the focus. So it's faster when it's closest to the body that it's rotating around, and slower as it moves away from the focus. C, goes faster when relatively straight and slower when turning. In an ellipse, you kind of have these long, straighter curves and then a much sharper curve. Or D, the opposite, it goes slower when relatively straight and faster when turning. So again, take your best guess on this. I know you don't have any background knowledge or anything really to operate off of, but we'll see how we're feeling. All right, we got at least 10. Okay, looks like we're pretty evenly torn between B and C, which is kind of interesting because they're sort of saying the opposite thing. B is talking about how it goes faster as it approaches, and so that would be kind of as it curves around, that it's going faster on the turn, kind of similar to what D is describing, and then moves slower as it fires outward. Here it's saying going faster, it's relatively straight and slower when turning. I mean, C and D are sort of vague enough that you could argue that either one could be valid, but what I was getting at here, the correct answer is indeed actually B, that the satellites are going to move fastest when they are closest to their center of orbit, whatever it is they're orbiting around, and they're slowest when they're furthest away from it. So to sort of give you an image of this, here's some more detail on elliptical orbits. Okay, so it's going to move fastest, the satellite, when it is closest to whatever it's orbiting, right? So that's when it moves faster as it approaches and passes the planet or the star that it's rotating around. Uh, so imagine sort of very big speed velocity arrows here going really, really fast. But then as it gets further and further away, it's sort of like the gravity of this, whatever it's rotating around, slowly pulls it back. It's almost like it threw it outwards, but then there's just enough gravitational force left that it's going to slowly draw it back towards that initial thing. So again, kind of smaller arrows here to indicate the slower velocity here. And you can find animations that kind of show this, that it like whips around and it slowly comes back and then whips around again. And they often refer to that as slingshotting. This is something that, believe it or not, like satellite engineers and NASA, they use to accelerate things that they fired into space. You can send them around a planet or something, and it'll fall into orbit temporarily, and it'll actually speed it up. And they're able to achieve escape velocity and go somewhere else. We'll talk about that in a second. But the moon follows an elliptical orbit around Earth. The moon has what's called apogee when it's furthest away and perigee when it's closest to our planet. And that's technically when it's moving fastest, and then it's moving slowest when it's at apogee. Does anyone know what this affects on our planet that if you're on the coast, you can notice?
Tides.
Yeah, if you ever heard of spring tides and neap tides, spring tides is when high tide is really, really high, right? When the water comes way, way up. And then you can also have what are called neap tides, where even though it's high tide, the water doesn't actually achieve a very high level. And it's because it depends on whether the moon is closer or farther away. Earth is also making a parabolic orbit around the sun. We have what's called perihelion, where we're closest to the sun, and I think it's called aphelion or aphelion, when we're furthest away. And it's sort of counterintuitive. I always thought when Earth is closest to the sun, anyone want to take a guess what season that might be? Would you think it's summer or winter in the northern horizon or northern hemisphere?
Summer.
That was what I was thinking, right? We're closest to the sun, that must be the summer. In reality, apparently summer typically falls when we're furthest away. And winter is more when we're closest, which seems counterintuitive. But remember that the seasons, summer and winter, actually have more to do with Earth wobbling, right? That the northern hemisphere tilts towards the sun, and then the southern hemisphere tilts towards it at another point in Earth's rotation. But anyway, I thought that was kind of interesting. So, all right, that's elliptical orbit stuff. Last question I'm going to ask you is geosynchronous orbit. This is actually a free response question, so you'll be typing an answer. Just want to see how this works. It's worked well in my other classes. So again, you can go to colaf.com, enter that address in and respond, or you can use your cell phone with those instructions. The question is, what is a geosynchronous orbit? Again, I know you don't have any background knowledge of this, so I encourage you to break down the word. What do you think geo means? What do you think synchronous means? And we're talking about something orbiting, so how is this describing orbit behavior? So take a guess and we'll review in a minute. All right, let's take a look. One option is how long Earth rotates its axis when planets orbit with a synced pattern or speed. So you're getting at what synchronized means. An orbit that has mountains move as the Earth moves. All right, I think I see it like on the surface. A satellite that is perfectly shaped to the planet it is orbiting. All right, we'll have to talk about what shape means. Center orbit, land or rock, a synchronized orbit, whatever object is in orbit, an orbit that moves synchronous to the Earth's rotation. There you go. A projectile with an orbit time that has the same as the orbit time of Earth. Good. Those are both good descriptions. Orbit is irregular, maybe. Geo-related Earth synchronous, moving at the same time. Nice. I like that you guys are breaking down these words here in tandem. Good definition for synchronous. So good. We definitely had some good descriptions there. And that's exactly, you guys are getting at the right thing, that it has to do with when the orbit of a satellite matches Earth's rotation. So to talk about this specifically, though, I've got to put something in context here about how we can alter the speed at which a satellite moves. So as we've been talking about, in order to fall continuously around the planet, satellites have to go pretty fast. And so looking at this image here, take a look at these satellites that move in what's called a polar orbit. See how they're pretty close to the surface of the Earth? It's not very far. They're not very high up. Technically, they're outside the atmosphere, but that's it. So satellites like that have to move very, very quickly. And in fact, they're moving so fast that they move around our planet like almost every 90 minutes. I mean, think about that. In an hour and a half, these satellites have gone all the way around planet Earth. It's a pretty insane speed. But if we're able to get a satellite further away, if you look at this satellite here that they call a geostationary satellite, right? This is a huge, huge distance. This satellite could actually move a little bit slower and still stay in orbit, right? It doesn't need such a high speed, and therefore it might not make a rotation around the Earth every 90 minutes, but maybe every like 10 hours or something like that, right? And so with that in mind, if we could slow rotation down enough to match Earth's rotation, then interesting things happen. And that's what's going on with geosynchronous orbit. So if we can get a satellite to be 5.5 Earth radii away, which is the equivalent of 22,000 miles. So if you see that dotted line there, you have to understand that represents about 22,000 miles of distance between that satellite and the surface of the Earth. But at that point, this satellite is able to stay in orbit. It can continue to move around our planet, but its orbit time, given the speed that it's going, it can go to slightly slower speed. It will take 24 hours for that satellite to make a full rotation. And I'm hoping everyone knows that. Does anyone know how long it takes Earth to make a full rotation on its axis?
24 hours.
24 hours. Fun fact, does anyone know, is it actually exactly 24 hours? Or is it a little bit more, or a little bit less?
A little less.
I think, actually now see, I'm second guessing myself, right? This is why we have a leap year. The reason we add a leap year is because Earth's rotation is, right, I guess it is a little bit slower, and therefore we have to add a day, or is it because it's faster? Now I'm doubting myself.
I think
Anyway.
it's because
Or
it's
that actually might be,
like the year doesn't actually quite equal a year.
yeah, that's right. That's more Earth's rotation around the sun, I think. Yeah, you're right.
Yeah.
It's actually Earth's orbit is not a perfect 365 days.
Yeah, it's not 24 hours. It's slower. It's 23 hours, 56 minutes, and 4 seconds.
There you go. So there's 4 minutes of time technically we're losing. But yeah, there's goofy things we do in our calendar, like adding a leap year and that sort of thing, that then try to adjust for that. But I think leap years have more to do with the rotation around the sun. But yeah, fun thing to think about. So, but yes, geosynchronous orbit, as a lot of you are getting at, is the fact that if the satellite's rotating in 24-hour in its orbit and it's matching Earth, then that satellite can stay stationary over that particular spot on the planet. And so that's geosynchronous, satellites that can stay above one spot on Earth permanently. So imagine if you had a satellite above your head, 22,000 miles up, which is an unimaginable distance, but it would be able to stay there. Now, Earth does wobble on its axis, so I think there is some correction that these satellites have to do to make sure they still stay over one particular spot. But this is what a lot of satellite TV companies and cell phone companies use, because they can essentially park a satellite above a certain region, like the East Coast of the United States, and they've got a satellite that's able to cover certain regions or certain spots there, and operate. So kind of cool to think about. Okay, so the last part of chapter 5 is talking then about, well, what if we went even faster, right? So far we know that 8 kilometers per second would give you basically a circular orbit. Going a little bit faster would give you an elliptical orbit. But what about if you were able to get out of orbit altogether? And that's what escape velocity, or the book calls it escape speed, but I prefer also to consider direction, right? Velocity also takes direction into account, and we're moving away from the source of gravity. And that could be horizontally, vertically, whatever. But if you wanted to get out of orbit completely, it depends on the gravitational force being exerted by the planet or the star, right? So Earth, it turns out, and your textbook has a long description about how this matches the energy needed to get, a projectile off the surface. But the point is that a satellite would have to be moving at least 11.2 kilometers per second. So if we could fire a rocket with that speed, or somehow throw a rock with that speed, that would escape from Earth and would not come back. It would not fall into orbit around Earth. It would not even go into an elliptical orbit. It is gone. But it turns out that even if you are able to achieve this speed, that doesn't mean that the satellite can then go wherever it wants, right? Because it's actually going to fall into the influence of what? Does anyone know what's holding Earth in place?
The gravity of the other planets and the sun.
Yep, other planets have an influence, but the sun in particular has a very strong gravitational influence, even at the insane distance that we are from it. We're a long way away from the sun, but it still plays an important role. So any satellite that is fired away from Earth, it can achieve 11.2 kilometers per second to get away from Earth, but it's going to have to speed up even more, 42.5 kilometers per second, if it wanted to exit the solar system, right? If it wanted to get away from the sun and everything. And NASA actually has done this. There's a satellite called the Pioneer 10, and I think there's a few others now too. But the Pioneer 10 was launched in 1972. It started very slowly. I think it took almost 10 years or more than that. I think in 1984 it passed Mars. And then they did sort of a slingshot thing, right? Where they, if you imagine, I think it was Jupiter with its rings around it, that they sort of sent the satellite directly around Jupiter and sort of used its gravitational force to speed up the satellite and achieve the added speed needed to get it out of the solar system. So now Pioneer 10 is in interstellar space. And as far as I know, they're not in contact with it anymore. It could crash into something, or maybe some other form of life will find it. Who knows? There is like a whole little arc of information about Earth and humans supposedly stowed away on it, which is kind of cool to think. But pretty crazy that you have to achieve these speeds in order to get away from the gravitational influence of things like the sun and Earth. And remind me again, what was gravity dependent on? Think of the equation. What is gravitational force directly proportional to? Mass, right? And so you can see that reflected here. The sun is by far the most massive thing on our solar system. And if you were close to the sun or on the surface of the sun and you didn't get totally vaporized, which you would, but you would not be able to escape either, right? It takes 620 kilometers per second. That's an insane amount of speed to try to get away from the influence of the sun. Now, luckily, we are a huge distance away, and so that has reduced the sun's gravitational influence, right? So that's just the 42.2. There's Earth right there, what we were just talking about. You got to have 11.2 kilometers per second to get off of the surface of the Earth. And what I think is interesting is then look at the moon, right? The moon has a very low required escape velocity, right? 2.4 kilometers per second. So if you think about astronauts, when they went to the moon, it took a lot more energy and fuel to get our astronauts off the surface of the Earth and away from Earth. But then when they landed on the moon and got back in their command module to take off from the moon, didn't need as much energy, right? It only takes 2.4 kilometers to get out of the moon's influence, and you won't be orbiting it anymore. You have escaped. So it kind of matches up with what we've been learning about gravity being directly proportional to the mass. So I know there's a lot of numbers that I threw at you. I made this slide as sort of a summary. So this is the key takeaway, right? That 11 kilometers per second, assuming no air drag in a horizontal direction. Like again, this drawing here shows them firing a cannon from the horizontal, and it's really, really high up on some kind of pedestal outside the atmosphere. If you were able to fire your cannonball at 8 kilometers per second, it would achieve this circular orbit around the planet. If we fired the cannonball with a little more than 8 kilometers per second, that would have an elliptical orbit, which they don't really show here, but it would look like this, right? It would rotate out and then back in again. And it would be moving a lot faster, closer to the Earth, and slower as it swung back. If we were able to fire that cannonball at least 11.2 kilometers per second, it would escape. There's your escape velocity. It would not fall into orbit. It would be on its way out into space. However, it would probably get picked up by the sun and just start to rotate around the sun, just like Earth is doing, unless it was somehow able to then speed up to 42.5 kilometers per second, at which point it could leave the solar system if that was the goal, or if that was the correct direction that it's going in. Okay, that is it for chapter 5. We'll be moving on to a chapter kind of more towards the end of the book, all about solar system stuff. But any questions on that or anything that I went over? All right, this will set us up well for talking about we're going to go into solar system stuff a little bit. I think it will be our next chapter. Okay, I want to use the remaining class time to get you going on your simple Rube Goldberg machines. If you go back to your Canvas tasks list, we are on task number 4, the simple Rube Goldberg machine. The first link is just a link to the project description. It's the same one I gave to you earlier. So if you need to reflect on the basic expectations, due dates, that kind of thing, that's all there. Hasn't been changed as of yet. I have instructions right below that link in the bullet points here, and the goal is to film a video of your simple Rube Goldberg machine and post it to Flipgrid. Here's what the Flipgrid assignment looks like. It's titled Simple Rube Goldberg Machine. I've actually posted the video that I made again, same one you watched when I introduced this project, and I've got the expectations here. The goal is to put together a simple machine at home that has at least, I think I was saying 4 or 5 unique objects, different kinds of objects interacting in at least 3 kind of unique ways. And you need to, at the start of your video, talk about what your machine should do, like walk us through it. Like, okay, this should hit that, this should move there, and then activate your machine and let it go through. It's okay if it's not perfect, if you've got to like give it a nudge every now and then, that's all right, but it should go into completion, right? You should have it go all the way to the end and then you're set. So those are the basic instructions that you should work on. Below that, I've got all the details taken from the project description and a link to the video again. But I want to give you a little bit of class time right now to at least start putting something together. I don't expect you to have the video done in the next 20 minutes, but maybe find a space, put your materials out, try a few things, but then you can post the video as homework as well. So it's 11:20 now, so I'm going to give us about 15 minutes to work on this. So we'll come back together at 11:35. So take 15 minutes to try putting something together. Again, you don't have to have the video done, but at least get started on it. If you do get the video done, great. But if not, don't worry about it. You can do it as homework. But we'll at 11:35, we'll come back together to kind of reflect on how things went, and then I'll just give you your homework and you're all set. So go for it. I'll see you back here again at 11:35. All right, everybody, the time is 11:35. Let's come back on into the room, please. How'd it go? Keone posted a pretty good video. I would definitely check that out when you can. Good use of a falling panda bear, and also Pickle Rick, which I recognize from our little Wilson TI Christmas gift exchange a year ago. So, all right. Most people feel like they've got a space and they've got the materials that they want to use. So what I want to emphasize is, as you roll into this and try to complete it for homework, the key word is simple. Okay, don't try to go crazy. You don't have to like fire a projectile from across the room or something like that. Keep it simple to start. This is meant to be fun, meant to be something to just play around with and get ideas. It doesn't have to work perfectly. But again, you might want to do multiple takes. You know, maybe you can get a better video than the first time you do it. It's going to take that sort of patience and resetting every now and then. And then once you've posted yours, or if you're having trouble coming up with ideas, check out the videos posted by others, and maybe leave a positive comment for them. And just think, you know, tell them what you thought was cool about their machine, but might give you some ideas then too if you haven't posted yours yet, or for your future one that we'll work on more in the long term. So that's all I wanted to share about that. I think just keeping it simple, and also the other thing that I've learned, and you'll learn this by playing around, is that you really have to have everything on a hairpin trigger. And what I mean by that is that if you're going to have something fall over, or if you're going to have something roll, it's got to be pretty close to doing that already, right? It's got to be pretty wobbly or like right on the edge. Those are the parts that will then work really well once you've started it, because everything needs just a little nudge, not something more powerful than that. Okay, so your only homework for Tuesday and over the weekend is to post your Flipgrid video, and also check out a few others and leave a positive comment. I would like you to read Hewitt chapter 5.12, which is the last section in chapter 5. There's no reading check questions this time. Just take some notes for an open notes reading quiz that you'll have for the do now on Tuesday. Okay, I will hang around here in the room if you have questions or just want to chat about anything else, but otherwise that is it for me. Thank you very much. Enjoy the weekend. Have a good one.
Thank you.
Thank you.
Okay.